Hey guys, Alexander here, and welcome to this video where I will be introducing you to the binomial distribution. So let x be a random variable that denoting the number of successes in n Bernoulli trials, with each trial having the same success probability p, and they are all independent. Then x will be distributed binomially with n number of trials and a success probability of p. So to put this into a framework that is better for associative learning, think of the binomial distribution as a useful model for modeling the number of successes, the number of heads that you flip in n number of coin flips. So let's say I'm flipping n fair coins. Then each of these coins can be a success, which will be a head with a probability p, which if it's fair, it means that probability is going to be a half. And there will be n such trials. Or say if I flip 10 such coins, then x will be distributed binomially with n being equal to 10 and p being equal to a half. So the binomial distribution, its probability mass function is given by, this is the PMF, the probability mass function. It's given by ncx times p to the power x times 1 minus p to the power n minus x, and it's valid for the support of x being equal to 0, 1, 2, all the way up to n. So what is the c? The c is simply a combination, the statistical idea or the idea of combinations, and its formula is n factorial over n minus x factorial times x factorial. And this is what combinations are for. And just as a reminder, 0 factorial is also equal to 1. So this is the probability mass function of the binomial distribution. Its expected value is n times p. So it's the number of times you flip a coin times the probability of each flip being a success or a head, as we have defined it. The variance of x is np times 1 minus p, but this is also usually denoted as npq. What we usually do is you say we let q, which is the failure probability, be equal to 1 minus p. And this just simplifies. It means we don't have to write 3 characters when we can just write 1. The moment generating function is 1 minus p plus pe to the t to the power of n, and it's valid for all values of t. But if you look again, we can simplify this as q, so it can also be q plus pe to the t to the power n. So let's look at an example of a random variable that follows the binomial distribution. If we let x be the random variable denoting the number of successes in 10 independent fair coin flips, with each trial having the same success probability, then what will be the distribution followed by the random variable x? So in this case, heads is what we define to be a success. Okay? So what distribution will x follow? Well, we know that n, the number of coin flips are 10. They're all independent, and they are with each being having a fair coin flip, so p has to be equal to a half. So that suggests that x has to be distributed binomially with n equal to 10 and p equal to a half, which it indeed is in this case, 0.5 being a half, of course. So what I want to draw your attention to here is that a coin flip, one coin flip, is equivalent to a Bernoulli random variable with a success probability of p. This is the same, we can say it is equivalent to a binomial random variable where the number of trials is 1 and the success probability is the same as p. So Bernoulli and binomial are related. Binomial counts the number of successes in a certain number of Bernoulli trials. The Bernoulli is a special case of the binomial, where we're only looking at the outcome of a single trial, a single experiment. So always keep this relation in mind, that there's an equivalence between the Bernoulli and the binomial distribution, because this will make your life easier when you are working with the binomial distribution. So what's the probability of getting exactly 5 heads? Well, that's just the probability that x is equal to 5. So if we look at this, this is based on our formula. It's out of the 10 flips, we choose 5 of them to be successes, as I'll term it here, and we have the probability of success being a half to the power of 5 times 1 minus a half, which is q, which is still a half, to the power of n minus x, which is 10 minus 5. And if we look here, this is indeed the answer. It's 10c5 times 0.5 to the power 5 times 0.5 to the power 5, which gives us the answer of 63 over 256. What's the probability of getting at least 2 heads? Well, that's going to be the probability that x is greater than or equal to 2. And if your calculator can plug in, has a summation operator, which I know Casio ES calculators, like the Casio FX991 ES Plus or so, they usually have this summation operator. So it will be the summation from 2 to 10 of 10cx times 0.5 to the power x times 0.5 to the power 10 minus x, which gives us the answer of 1013 over 1024. But let's use our head and think of this. We want at least 2 heads. At least 2 heads is the same as saying, well, what don't we want? We don't want 0 heads and we don't want 1 head. So we can also use the complement. We can say 1 minus the probability that we have less than 2 heads. So this probability that x is greater than or equal to 2 is equivalent to 1 minus the probability that x is less than 2. And this is just the summation from x is equal to 0 to x is equal to 1, which is much easier to calculate. It's simply the probability of having 0 successes plus the probability of having 1 success. This is much easier to calculate by hand than to do all of this summation from 2 to 10. So always read a question carefully and see if you can apply an idea that you have already learned or a concept that you are familiar with. Such in this case, we are using the idea of a complement to simplify our calculation. That is to say, we can split the probability space if this whole space is equal to 1, which is all the things that can happen. Then we can split our space like this. This is having 0 heads and having 1 head. This is all the events where we have 2, 3, 4, up to 10 heads. Okay? So this area summed with this area. So let's have it a plus b must equal to 1, or a plus a complement is equal to 1 in this case, because we only have these events that exhaust the entire sample space. Then we know that if we are interested in finding b, well, b is just going to be 1 minus a, or a complement will be equal to 1 minus a in this case. So use concepts or ideas to simplify your calculations to make life easier for yourself. Always think before answering a question. Think of how can I do this in a better way. I hope this has proven to be a useful introduction to you for the binomial distribution, and that these examples have given you some idea about how we go about using it. And as a last takeaway about this video, I want you to always have the association between the Bernoulli distribution and the binomial distribution, and specifically, again, the coin flipping example. Binomial distribution counts the number of successes, or the number of, however you define your success in this case, let's define it to be heads. It counts the number of heads in a certain number of coin flips. So the number of heads that resulted from a certain number of coin flips, n such coin flips usually. Thank you very much for watching this video. Boer Commander out.